video, we are going to learn about vectors and tensors. These two concepts are somehow related to each other, but there is an amount of difference. There is a difference in the understanding. So in today's video, I'm going to talk about the introduction of the concepts of tensors, how it is related to vectors, why do we need tensors at all, what is the role of tensors in physics, and how the understanding of vectors and tensors are related to each other and what is the difference between them. So I am keeping aside the mathematics of tensors away from part 1 of this video. However, I would be showing certain illustrations, certain notations and indices so that you can learn more about the concept of tensors as you go through your study in physics and mathematics. In this part 1 section of today's video, I would be giving a basic introduction but very important concepts on vectors and tensors and the need for tensors in physics and what are the notations and other different things. I would request not to skip this video because each of the chapter are related to each other. Vectors and tensors are the most important concept in both physics and mathematics. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first part of vectors and tensors. So before we go ahead, let us quickly look into what are the topics that we are covering. So we are covering this topic sequentially. First we will learn what is a vector. Then we will learn what is a tensor. Also we will understand what is the need. Actually, why do we need tensor? What do tensor actually helps us? What are the different types of vectors? And the understanding of the components of vectors are somehow very closely related to the understanding of tensors. And we will also learn the different notations of vectors because in each textbook of physics and mathematics there are different notations which are being used and the students get confused. Having said the topics, let us start our journey into vectors and tensors. So first let us understand what is a vector. Now, with the dawn of human civilization and with the advance of science and technology, the most important thing which mankind has ever designed is what is called measurement. We always try to measure, isn't it? We try to measure the velocity of the wind, we try to measure the temperature, we try to measure the way the car is moving, everything is being measured. Now, this measurement comes, say for example, here's a stone which is weighing around 60 kilograms of weight. And we know this stone has a certain mass. Now, if I put the stone on a certain place and if I try to measure in which way the mass is differing at all, on the east, west or north or south, we will find that the mass remains constant everywhere. Whereas I am standing right here and I am trying to find out whether my weight is moving either east, west, north or south, and what I am finding is that my weight always remains constant. So we need something here that the direction is not required, and that is what we call scalars. So scalars are quantities that are fully described by a magnitude or numerical value alone. For example, 60 kilograms of weight of this stone. The word scalar comes from the Latin word scalaris, which is an adjectival from scala, which means the Latin ladder, from which the English word scale also comes. Now, if I am standing on this ground and I will see that there is a force acting downwards, which is say for example 10 newtons, and I can understand that the gravitational force is acting downwards. So a force of 10 newton is acting in the downwards direction. For certain quantities we require to join the direction along with their magnitude to describe them. So earlier the example where we just need only the numerical quantity just to describe the kilogram of it, but here what we need is both the direction and the magnitude, and this is what is called vectors. So it comes from the Latin word viher, which means to carry, and a vector is the mathematical representation of a physical entity that may be characterized by size, which is the magnitude, that means how big it is or how small it is, followed by the direction. So a scalar, on the other hand, is the mathematical representation of a physical entity that may be characterized by magnitude only. That means one part is only magnitude, which is given by numerical value. Here it is both the magnitude and the direction. We all know this. Now why I'm repeating that? this concept will become very clear. Now from here, when we move into something which we call a tensor is the mathematical representation of a physical quantity that may be characterized by magnitude and multiple directions. So you see the difference which carries between a vector and a tensor is that the multiple directions were not there in a vector which is present in a tensor. So I can talk for example x as something which is a scalar, or I can say x1, x2, x3 as a vector, or I can write in this kind of a matrix form. But here is a tensor, right? So here for example x11, x12, there's a first element of x followed by the first element of x, and the second one the first element of x, and the third one. So this is how a tensor looks like. And for a second rank tensor, which we will learn slowly what is a second rank, third rank tensor, you can just understand that 3 square is a second rank tensor. It comes for 9. 3 square is 9, and for an n dimension space it would be n times r. So a scalar may be represented by a single number, a vector may be represented by a sequence of three-dimensional space, but a tensor may be represented by an array of 3 times r numbers in a three-dimensional space, or we move into 4 or 5 or n-dimensional space. So this is the first definition, or where we encounter what is a tensor. Don't worry, things will become much clearer once we go ahead in this video. We will give multiple examples of tensor, and we will show you really why there is a need for the tensor, and why physics is so much all about tensor, and why we are learning tensor. So when till now what we have understood is that when there is a question of multiple directions, magnitude and multiple direction, this is where tensor comes in. Tensors look like this: x11, x12. We got one scalar, we got one vector, and we got one tensor. Okay, so let's move ahead in the video and let us find out more about tensors. So you see, a scalar does not have a subscript. This is very important. A vector will have more or less a single subscript, but you see the tensors might have 2 or more subscripts. Now why 2 or more? I will just show you a illustration and things will become clear. Now you see, this is a kind of a stress tensor. Okay, let us name it any kind of a tensor. It is called a triad. Now what is a triad? Which has got 3 indices. Let us understand for this right now. There might be dyad, there may be n number of things. So triad and dyad, these are the numbers of scripts which are required to measure something. We will soon understand what it is. Now you see here, this is a tensor of rank 3. So you see here in the figure on the left hand side, sigma followed by xxx. Then again tau followed by xyx. Now what do we mean by those indices? We will come later. For the time being, let us understand this is a tensor of rank 3. That means it is measuring something in 3 dimensions. So here you see sigma followed by xxx. Something, there are 3 subscripts. So that is again something which is new for a tensor, which is not in a vector. So tensors will have 2 or more subscripts. Now the next thing which is a question in our mind is that when we are dealing with those vectors and subscripts and all those things, we know that it is the tensor of rank 3. Now how actually the tensor behaves, how actually it comes into, and what is that we should know tensor, without which is it that life is not beautiful? Let us find it out in the next part of our video. So you see, this is a kind of a summation. Scalar is any physical quantities which have only magnitude. You do not need to bother about direction. Vector are physical, any physical quantity which has magnitude as well as direction, and tensor any physical magnitudes which have magnitude as well as multiple directions. Now say for example, this is a kind of an illustration which is a kind of a stress tensor. Now if you know engineering, or you have been to mechanical engineering, you will understand that stress doesn't happen on a cube from one direction. It has got different direction. Same happens when you are measuring the stress, or when you're analyzing a crystal. Isotropic and anisotropic crystals will have stresses and measurements in different direction. So this is something which is called a tensor, because tensors are simply mathematical objects that can be used to describe properties, physical properties, just like scalars and vectors. And the word tensor comes from the Latin word tender. You call this tender muscles or tensions, etc. That means to stretch. So sometimes your muscle gets stretched, so the word tensor is stretched. And it is really justified because from the word tender, it means to stretch. And you will see that as we will learn, tensors are basically stretching. We are stretching the concept of vector into multiple direction, and that is how tensors come into being. So it is well justified from the Latin word tender, which means to stretch. We are stretching the concept of vector from one direction, particular direction, to multiple direction. Okay. Now here we will come and try to understand that what is actually a tensor. These are mathematical objects which is not only used in physics but also in mechanical engineering. If you go into fluid dynamics, I mean to say it is a super important concept, and I'm trying to give you a basic fundamental concept of what is a tensor. Okay, first I will try to define you what is a tensor it is. It's just a kind of a literal definition you can just understand very in simple language. So tensors can be defined as an algebraic object, and it is called multidimensional arrays. We have just seen the stress tensor have got XXX. So these are multidimensional arrays. Mathematical objects that can be described to describe physical properties. Obviously, these are mathematical objects. Why? Because we need to describe physical properties, right? So tensors defined mathematically are simply arrays of numbers or functions, and in simplest form, it is a quantity having magnitude, direction, and plane to act are called tensor quantities. That means it has not only got a magnitude and a direction, but we have to say on which plane it is acting. That is on the back side, on the front side, on the left side, on the other side of the cube. I will just show you a physical representation, and you will see why tensors are important, especially in terms of relativity. So you see, this is something which I have dealt in very much details in my, if you go to my playlist, which is called General Relativity. This is a kind of what is called a metric tensor. Now, what is a metric tensor? For the time being, let us understand metric tensor is something which measures the causal structure of space-time, a central element in Einstein General Relativity. And here, the metric tensor is symmetric. That means if I change the subscript from g mu nu to g nu mu, it will be the same. So metric tensor, it is again a tensor. Very important property of general relativity is a symmetric tensor in bilinear form. And this mu nu actually denotes the dimension of space-time. That means this particular mathematical object, metric tensor, has got a huge amount of information. Lot of information are stored in this metric tensor, and it is important for us for measurement. And in the coming few minutes, I will tell you why it is so important. So this G01 equals to G10 cancels out, G02 equals to 2, G20 cancels out, and ultimately it leads to just this 10 forms. So you see 4 plus 3, 7, 8, 9, and 10. So that is why it is called, it is a symmetric tensor, because some of the properties cancels out. So this 16 property of metric tensor ultimately reduces to 10 properties. I have dealt much more details, not only with metric tensor but with stress tensor. If you want further details, you can go into my playlist. You will see there is one video which is called Importance, or I remember the name as the role of tensors in general relativity. Yes, there's a very important video which explains out clearly the entire role of tensor in general relativity. Okay. So you see, even tensors are there in Einstein's field equations, which dictates the entire general theory of relativity. So you see, this R mu nu is called Ricci curvature tensor. R is called Ricci curvature scalar. G mu nu is called the metric tensor. Lambda is the cosmological constant. G is Newton's gravitational constant. C is the speed of light. And T mu nu is called the stress energy momentum tensor. Now, this is not the right time that we will explain what are the meanings of each of these tensors, because again, it has been explained quite details in multiple videos in my playlist in general relativity. But this R mu nu, G mu nu, and T mu nu are the three tensors which are there, and there is one hidden tensor which is called the Riemann curvature tensor. I'm not going into that. So you see the importance of tensor. It is there in Einstein's general relativity, and it shows how space-time is curved and how do we measure the curvature. We will come to that. We will soon see that why the importance of tensors are there. Now this is something which is called the stress energy tensor, sometimes called stress energy momentum tensor, or the energy momentum tensor. This is a tensor, a physical quantity that describes the density and flux of energy and momentum in space-time, generalizing the Newtonian stress tensor into relativity. It is an attribute of matter, radiation, and non-gravitational fields. So this part measures the momentum density. This part is also the momentum density. This is the energy density. This is the shear stress, and this is the pressure. And this is called the momentum flux. Okay, again, I have dealt all those elements in detail in my video in general relativity. What I'm trying to show you is that this is also a tensor. That means it encapsulates, it stores a huge amount of data. So here you see, I have written that every part of energy in universe that we think in some way, either this is pure energy, rest mass, stress, has found its place in this stress energy momentum tensor. That means the measurement of each and everything which we are doing in terms of scalar or vector are much more magnified and much more stressed and much more elaborated in this tensor. Now, yeah, so this is what is called the stress energy momentum tensor. Now you see that I will try to summarize what we have learned for tensors till now. Tensors are mathematical object which is invariant to any coordinate transformation. I will come to that. Don't rush. What is the meaning of invariant? However, the components change in a special predictable manner. We also know that this predictable way of changing helps us to do measurement, especially in curved space in Einstein's general relativity. And the cornerstone of general relativity is a tensor. As we move from flat space to curved space-time, measurement along the curvature is being done by a tensor. Okay, now the first important point in all those three definitions is the first one. What do we mean by invariant to any coordinate transformation? And what is the meaning of the component change in a special predictable manner? That I'm going to talk in the next part of the video. And the entire concept which you're talking about tensors, the utility, and why do we do it, it will become clear. So we come to the next important part, which is called the components of a vector. And in this part, I will be clearing out the components of vector, also the concept of tensor, and why tensors are used in measurement and what do they actually do. Okay. First of all, this is something very standard. This will be useful both for vector understanding as well as tensor. Let us take a vector something like this. Okay. Now, we want to divide this vector into small parts. Now, you might ask me a question that why do I do that? It is required for measurement. Say, for example, we are given a very big number. So, if we divide that big number into small parts, addition, multiplication, other mathematical operations becomes easier. So, I divide the first 4 parts, 1, 2, 3, 4, into this green vector, the next 4 part into this blue vector, and the next blue 4 part into a purple vector. I'm ignoring the upper 2 parts. I'm just considering these 4. So what I can tell is this this black long vector composed of 4 units of green vector, 4 units of blue vector, and 4 units of purple vector. So to total, it makes up the entire vector, right? So components of a vector are the pieces that can be used to make up a vector. The components of vector helps in the division of given vector in parts that are oriented in different directions. And as I told you, it in order to facilitate the execution of numerous arithmetic operations involving vectors. So we now understood that a vector can be divided into small parts. Now what will happen if this vector in a certain coordinate system suddenly changes? I mean to say the coordinate system or the coordinates it changes. Okay, let us see this. So we got a blue vector on the y direction, a red vector in this, the red is the vector, and in the x direction we have got the black vector. So we're trying to measure this vector. So what we can do is that, you see, we go 2 steps. We are trying to make up this vector, right? We are trying to, I mean to say, construct a vector made out of small vectors. Then we go a little bit up using this red vector, and then we connect using those blue. So on the x-axis we go with the black, then a little bit towards the red, and then blue. So what we can again tell is this vector is made of 2 units of black vector, 1 unit of red vector, and 2 units of blue vector. Now what I'm going to do is that I'm going to go for a little bit of change in the coordinate system. It won't be the standard Cartesian system. It would be like this. Okay, you see things are a little bit tilted, changed. Now even I can make the same vector part by part. How? Here I would require 2 units of black vector, 3 units of red vector, and 1 unit of blue vector. So 2 units of black plus 3 units of red and 1 unit of blue makes up the vector. Now, have you noticed a very important and a significant part is that the vector, that the red, or you can say that this black one, remains invariant. What changes are the components of the vector. So in one way we need two black vectors and one red vector, but here when the coordinates change we need two black vectors and three red vectors. Instead of two blue vectors in the first case, we are requiring one blue vector. So the essential understanding is that in case of Einstein's relativity, or when we are moving from one coordinate system changing to another coordinate system, the vector should remain the same. Otherwise, how will we measure the system? But what changes is the components of the vector, and this change is something which is registered by tensor. Okay, I will give you a better example. Say for example, this is the flat space and this is the vector A, and we are constructing the components AY in the Y direction, AX in the red direction, and we get something like this, right? Now from this I will be changing to a curved space-time. So I plot this and then I plot this one, which is curved space-time. Now when we are plotting the same A and we are trying to construct the vectors A prime X for the X direction, A prime Y for the Y direction, so what we get is that A prime X obviously is longer. You see the figure on the right hand side, AX, A prime X is longer. A prime Y is also longer in a curved space-time, but A remains invariant. That is what the components of the vector features, and that is how the components of the vector helps in. Same example, we take something like this one AX and AY, and we rotate the system here. So we rotate the entire Cartesian system. You see the A prime X again has become longer, and A prime Y in other terms has become shorter. So this is the static frame of reference and the rotated frame of reference. So the entire idea of giving these examples is to let you know that the change happens not with the vector but with the components of the vector. I'll give you another simple example. You see that these are the different vectors, so OA, OM, and this is the one, and then we plot. These are the components of the vector. You can say the components of vector are projection on the main vector, and xi hat, yj hat, and zk hat. If you don't understand what our hat is, don't worry, I'm coming up. So we can now say the entire OA is equals to xi hat, because that is the unit vector, and OB as yj hat, that is again a unit vector, and OC as zk hat. And I can write this entire radial vector R, which is equal to OM, equals to the addition of these three components, xi, yj, and zk. So as you see, the components of a vector is basically a help in the division of a given vector into parts that are oriented in different directions. So it is sometimes necessary to divide a vector into its constituent parts in order to facilitate the execution of numerous arithmetic processes, including vectors. When a vector has components, each component represents the portion of the vector with respect to each of the axes of the coordinate system. When a vector is in a three-dimensional geometric plane, it is possible to compute the components of the vector as well. So this is why the components of the vector are important. Okay, now because the components of the vectors are important, now you can understand that in case of a tensor, how these components are being added up, and we can understand the curved space-time. Okay, now it is a time also to get hold a little bit about the different notations of the vector. I mean to say different books have different notations, so I will try to give you a quick idea so that you don't have any confusion. In general, vectors are noted by V arrow. Now mind it that it is always not an arrow. When we go into abstract algebra, we will see that vectors are something more abstract, but that is okay. It is also considered to be something as bold, and it is also given as V underline and overline. So if you write something like x is equal to Vm, so the vector would be this capital V, right? So the magnitude or length of a vector is given by two double bars, and unit vector is one which has given a length as 1, right? So it is given as length as 1. So sometimes a vector may be located in a rectangular coordinate system, which is denoted by angular brackets, this or this, right? And an alternative way of writing it is this one, I equals to 1, 0, j equals to 0, 1, which leads to v equals to 6i plus 3j. So in general, it is an arrow, most of the cases in the textbooks. Some textbooks measures as bold, right? Unit vectors in Maxwell's equation otherwise are always given by hat, and the underline or the oval line is not mentioned. It's not very common, right? So a vector with fixed initial terminal point is called a bound vector. Bound vector means it has a fixed point, so you can see A starting the red one and it is extending up to B. So since a position vector does have a defined starting point, magnitude and direction, then it is a bound vector. If it is in the negative direction like this, it is minus A, quite simple. And there is something called free vectors. Free vectors are not bound vectors. They are not fixed to a point nor a line, and sometimes they can move freely around the space that has a fixed magnitude. So you can move a free vector anywhere. Something like this is not a perfect illustration, but anyway, so you can move a free vector anywhere you would like. Okay. In general, represented as this, but these are ways. When you see these arrows moving in certain directions like this, like this, like this, and like this, these are called vector field. Now, I'm not going to go much more into the mathematical derivation of a field, but what you can understand from here is that a vector field issues a vector to each point in space, thus allowing us to represent physical occurrences. For example, the spinning effect of a merry-go-round or the sloshing of your morning cup. That means multiple lines, multiple things. It can be a fluid, it can be a wind, it can be something which is represented by the vector field. So this is, you see 3 and 4, this is an individual vector, whereas this one, each point in two-dimensional space is associated in two-dimensional vector. So when we're talking of vector field, essentially, say for example, we are talking of fluid dynamics, this single arrow is now being bifurcated or magnified into multiple direction, and that is why we call it a vector field. A vector field has got a lot of mathematics, including partial derivatives. I am not going into that, but let us understand what this vector field is all about. Okay, so these are parallel vectors. Now, parallel vectors are something which are has got the same length or same equivalent. So each of these all represent the same vector A, and a vector representing the movement from opposite direction, that is from B to point A, would be in the opposite direction but have the same length. So this is the definition of what is a parallel vector. It can be in the positive or the negative direction. It can even be scaled. For example, this vector A can be multiplied and scaled into 2A. That is through multiplication. That we will come later when we will learning the operations part of vector. Okay. So now let us understand what are the different types of vector, and there are multiple types of vector, and each of them has got a very important significance in our understanding of physics and mathematics. The first one is called a zero vector. Nothing much to tell. When the magnitude of a vector is 0, the starting point of the vector coincides. So just a point is called a zero vector. You know what is a unit vector, which has got a length 1, which is generally denoted by hat. So you see these are on the left hand side, you see I, J and K. These are unit vectors. That means it has got length 1, and the unit vector V having the same direction as V is given something like this, equivalent. So this is just a kind of a understand. This is the kind of formula and through which we understand. So we understood zero vector. We then go to 1, which is a unique vector. So this is an illustration which I am trying to show you, that it just measures the length, which is 1. So what are the next types of vector? One is a position vector. This is extremely important for mechanics. Position vector simply denotes the position or location of a point in a three-dimensional Cartesian system. So you've got an origin and it is an object is positioned towards this. The second which we have got is called equal vector. Equal vectors means two or more vectors are said to be equal vectors when their magnitude is equal and also the direction is the same. So you see A, B and C almost the same. So we can say A, B and C, D are equal vectors. We come to the next, which is called negative vectors. So if two vectors are the same magnitude but exactly opposite direction, something like this, this is called a negative vector. AB equals to the negative of CD. And something we have got called a collinear vector. These are vectors that lie on the same line or parallel lines are known to be collinear vectors. So they are also known as, you can say, parallel vectors. So this is simply the same direction and the negative is minus A. So what's up next? Co-initial vector. This is a very important concept. The vectors which have the same starting point are called co-initial vectors. So you see AB, this one, AB and AC, these are co-initial vectors because I've got the origin as O. There are like and unlike vectors, not very common, but anyway, worth taking a note. The vectors having the same direction are known as are like vectors. On the contrary, the vectors having the opposite direction are said to be unlike vectors. Okay. So what we find next is what is called a coplanar vectors. This is very important when you're doing dimensional analysis in three-dimensional space. It looks like this. That means they lie on the same plane. And there is another which is called a displacement vector. The change in the position is known as displacement vector. So you see from here, when we move from A to B, there's a change. And this change is being denoted by displacement vector. We'll take some very quick examples of displacement vector. For example, the positions of A and point B are given as 5A plus 3J plus 4K. So, and B equals to 2I plus 2J plus 1K. And this is how we just subtract 5 minus 2, 3, 3 minus 2, 1, and 4 minus 1, 3. Remember, the hats actually denotes these are unit vectors. So the displacement of an object can also be defined as the vector distance between the initial and the final point. Okay, so this is something very important, and most of the students confuse between orthogonal and orthonormal vectors. Orthogonal vectors, we say that the two vectors are orthogonal if they're perpendicular to each other, and the dot product should be 0. So here the vectors are perpendicular. We take A dot B equals to 0. I will just quickly show you, if we take a set of vectors, are these vectors orthogonal or not? I mean to say, what is the check? So we take the dot products of this, this, and this. And we see all the dot products are 0. That means these are orthogonal vectors. So it's a simple one condition that it should be perpendicular, that is the dot product should be 0. However, there is another concept which is called an orthonormal vector. Orthonormal vector has two conditions. One is that it has to have a magnitude, it has a magnitude and mutually orthogonal, right? Okay, so magnitude 1 and mutually orthogonal means that they should be 90 degree and they have a magnitude which is 1. So u dot v, if I take the dot product, it should be 0, and this it should be u should be 1 and it should be 1. So the difference between orthogonal is that it should be perpendicular. Orthonormal, it has to be both perpendicular and has a magnitude of 1. Okay, there are a few more vectors called concurrent vectors. That means they are passing through the same point. In other words, a concurrent vector is a set of two or more vectors whose line intersects. So you see the origin, both of them concurrently are moving to each other. Okay, so we have learned 13 vectors, 1, 2, 3, 4 up to 13, and each of them is very important. I hope this gives you clarity in understanding what are the different types of vector, and in case these terminologies or the figures are coming into your learning of physics and mathematics, things will be quite clear. Okay, time to summarize today's video, right? So we have understood what is a vector scalar. Most importantly, we have understood what is a tensor. We now know why do we use tensors, because those the changes which are happening on from a flat space to curved space, the vectors remains the same, the components change, and that is what the tensors registered. They try to measure a special predictable way, a rule through which it changes. How tensors are different from vectors? Because vectors have a specific direction, it is called multiple direction tensors. Usage of tensors in relativity. We have also understood how the components change, what's the invariant nature of a tensor, different notations, different types of vector, and most importantly, the difference between orthogonal and orthonormal vectors. So this concludes today's video. It is just the starting point. So you can keep watching this series where I will be talking mostly about vectors, and vis-a-vis I will be also talking about tensors. So vectors and tensors would go hand in hand with a lot of example illustrations, and I will be waiting for your comments. So please do subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students, and let me know your comment about how these videos are coming to use, and if you need more, please let me know in the comment box. Thank you for watching this video. We'll be back very soon with another interesting video. Till then, goodbye.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment, or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram, and LinkedIn. See you soon in the next video.